to gather the data we want to work with. We did all of this discussion back at the beginning of the term about getting information and getting data, collection and surveying and so on. If I have a population, I'm not going to find out what's going on in the entire population. I'm going to take a sample, especially in large populations, rather than do a complete census. I can then use the sample and make statistics out of that. So a sample statistics comes from taking some random sample of the population. Gather information, use a random sample, and then compute something. Whether that something is a mean, a proportion, or something else, I get information about my sample. There's just one problem. This idea of sampling variation. Page 273. Here are the GMAT scores for a whole group of MBA students. There are 2,637 scores here. Now, the GMAT is a computer-delivered exam, so I can actually get the information for the entire population. But this is for MBA applicants across the country. This was one seating of this exam, like the SATs, right? They offer them at multiple points throughout the year. So you take the SAT, you take the ACT, you take this to go to grad school in law, in business. And here is the entire thing. But Seton Hill only gets a certain number of applicants. So let's suppose I reach into the pile of applicants and I pull 5 of them. And I say, okay, what's the average score for these 5 people? What's the average score? Throw those back in the pile, stir the pile up, pull another 5. What's the average score for these 5 people? I can do this over and over and over again. So the mean for the whole group was given. It's 520.78. Then I pick up my group of 5. That top line represents the first group of 5. And there's a little red triangle in there. And that red triangle is the average of those 5 numbers. It's not exactly 520.78, is it? Same thing with the second line. Here's my next group of 5. It's got a slightly lower average. Next group of 5. Next group of 5. Next. You see how these vary from group to group? I have no control, because it is a truly random sample, over which 5 I get. But I can take the averages. Now I have 8 pieces of information, right? I have 8 averages, and I look at the distribution of those. And that's this down here. And that seems to cluster around the global population average that we were expecting, 520. It might be a little lopsided to one side, but it's closer than these individual averages are, right? So what we have here is an example of variation from sample to sample. One of the ways we can combat that is to look at the sample averages as if they were items. There's less spread if I look at the averages of my samples. Well, the averages from each sample rather than the entire sample itself. That's the variation from sample to sample. We can actually think of it as a sampling error. Okay. For any given population, what do these two symbols represent? It's average and mean, right? Those are the same thing, aren't they? So why are there two different letters?
One's for population, for sample.
Aha. The mu is the population average, and X bar is our sample average. So that was one red triangle in the list on page 274 when I look sample by sample. X bar changes from sample to sample to sample to sample, right? I pick a sample of 5 people from this giant pile of average of GMAT exams, and I get an average of those 5 scores, but mu is for the whole pile of scores. It's not going to change. This is variable, this isn't, within a particular population. Well, if something varies, then it's got some sort of distribution. Gesundheit. So I can think of X bar as a random variable. And maybe it's a uniformly distributed random variable. Maybe it's a normally distributed random variable. Maybe it's exponentially distributed. Maybe it's something else, but it's got a PDF. And now I can use what I know about PDFs. And I can estimate things about the population from things about my sampled statistic. Because that's what X bar is. It's a statistic we calculated from our sample, a sampling statistic. But there are 4 different possible sources of error or variability showing up here. I can't control sampling variation. I have no control when I do a truly random sample, even if it's a simple random sample or a stratified random sample or some sort of regular random sample. I can't guarantee any sort of control over the variation within the sample. I can't tell you what the population distribution is going to look like. I don't have any control there. So there are 2 things that are uncontrolled variation here. However, smaller samples are likely to vary more wildly than larger samples. If I take a really small sample, I only pick 3 people. I'm not going to get a very good look at the whole 2,367 from just 3. So if I take a larger sample, I might get a better view of what's going on. But I can control my sample size by choosing how many people to survey or how many objects to pull off my production line to run tests on. I can control that. That's why it's a source of controllable variation. I can also ask, all right, how sure do you want to be? This isn't a jury trial. I don't need proof beyond a reasonable doubt. I need to have some level of confidence in the answer I come up with. Give or take a little. That confidence behavior. How far off am I allowed to be and still call it okay? Is something I can choose. And it depends on situations that I'm dealing with. One of my favorites, I think I've mentioned it in this class before, is talking about rebar and concrete, right? I am going to take and build a building. You're going to have concrete floors. You have to put steel bars in there to keep the concrete in place, reinforce them. Diameter of the rebar I need is exactly 1/2 inch. Exactly? Well, that's what the spec calls for. It calls for 1/2 inch rebar. So I go down to Home Depot and I buy rebar and I start measuring it. And I get 0.498 and 0.501 and 0.497 and 500. I got one that's exactly 1/2 inch and 502. And it's not exactly a 1/2 inch, but how far off am I allowed to be? Well, my structural engineers will tell me I'm allowed to be off by up to 10 millimeters. No, 1/10 of a millimeter, right? Half, 5 centimeters, give or take 1/10 of a millimeter. I think that's right. So 502, 5.1 I could get away with. 510 in millimeters. So I can get the right give or take there. But if I say, well, let's look at a different situation. And in this situation, I'm looking at 2x4s. And how big do they have to be? They have to be 8 feet, give or take 2 inches. Well, now I have a different confidence level in my measurement. Questions? These things I can control. These I can't. What we're really doing is using the information from our sample to estimate things about the population. And in general, we're just going to call such a thing an estimator if I compute some sample statistic and it's designed to be a representative of a parameter that would have been found in the population. We were talking about means, right? Average is a mean. The mean from a population is a parameter. That's why I got a Greek letter. But the mean from my sample is trying to estimate that. So I think about X bar as an estimator for mu. In the same way, I can think about a proportion as an estimator for the proportion within a population. We did this with our binomial experiments, right? I needed some sort of chance of success. And standard deviation and variance are estimators for the corresponding population behavior. Now, the process of inference is where I draw a conclusion about my population based on a sample statistic. We talked back in chapter 4, where we did mean and mode and median and quartile. We talked about descriptive statistics. Most of what we're doing from here on out is usually referred to as inferential statistics. We're drawing conclusions from our estimators. Questions? There are some things I would like to know about what the calculation I do to create an estimator. I'd like my estimators to have some nice properties. So, again, I'll pull a population idea out of thin air. I want to estimate height of an undergraduate student on the Seton Hill campus. What am I going to do? I'm going to grab a bunch of people, measure their heights, take that average. And then I'll say, okay, based on this group, I think the average height of a Seton Hill student is. But we talked earlier about expected value from a probability distribution, right? My X bar, my average, is a random variable. It's got a PDF. It should have an expected value. Let's just pick a letter for the moment. We'll use T is an estimator for theta. That way my estimator is a Greek letter, a regular letter, and my population is parameter is a Greek letter. Sorry, a Greek letter, Roman letter. That's what I wanted there. I'm going to call the bias of T is the expected value of T minus theta. Yes, ma'am.
Value?
Yes.
Okay.
It's okay. Crappy handwriting day. Now, since most of the time I don't know the exact value of theta, but I can compute the value of E of T, I don't necessarily know off the top of my head bias of an estimator. But my hope would be that I can create an unbiased estimator. If an estimator is unbiased, what does it tell you about the thing we just compute here? Hmm. Greek letter theta. That's our parameter. And so that's our parameter and that's our sample statistic. Rather than just pick one like X bar and mu, I was trying to do it in general.
But the expected time is the bias.
But if it's unbiased, if T is an unbiased estimator, then that difference should be zero. But since T is calculated each and every time, what that means is on average, if I do a bunch of different samples, some of them will be high, some of them will be low. Maybe every now and then I'll get one that's right on. But they should just as likely be high as low. If I go out and I estimate the height of a Seton Hill student by grabbing 5 people, I could grab 5 ladies off the volleyball team. I'm pretty sure they're going to be tall. I could grab 5 guys off the wrestling team. They're probably not tall the same way. I could grab 2 of 1 and 3. My average could be low, could be high, but if it's an unbiased estimator, it's just as likely to go in either direction. Does anybody here target shoot? Regardless of what you shoot with, a bow, a gun, whatever. Picture target shooting. If you're an unbiased shot, you might not hit the bullseye every time, but you're just as likely to pull left or right or up or down as any other direction. If you're biased, what would I expect to see on your target?
Leaning towards one way or another, up, down, left, right, just all of them.
Aha! I'm not perfectly on target every time, but I miss in any given direction. That's unbiased. Clearly in the right picture, I'm pulling right. Whatever I'm doing, I'm pulling right in that shot. Maybe I need to adjust my sight. Maybe it's a motion I make as I pull the trigger or let go of the bowstring. Whatever it is I'm doing. Baseball players do this a lot. Where am I going to, this guy's left-handed, where's he going to hit the ball? It's going to go between these 2 fielders every time, right? They pull in one direction based on handedness. Or this guy's early on the swing or late on the swing, and I'm going to continuously see him hit to right field or left field because of it. I would like to find unbiased estimators as often as I can. Now, we'll have to figure out a method by which I can check to see if an estimator is unbiased. But I'd like to design estimators that are, at least if they're biased, the bias is as small as I can make it. Now, unfortunately for us, finding out how to minimize something is a calculus concept. So there is actually a calculus way to decide how small the bias is for a particular calculated estimator. We're going to put that aside, and I'm going to guarantee you that that's a topic for the calculus-based statistics course that none of you have to take. It turns out average and proportion are unbiased estimators. Unbiased, goodness, estimators for mean and proportion, respectively. But standard deviation is not. Standard deviation is biased. STD EVP. Remember, we said there were two standard deviations in Excel. There was the population standard deviation, and there was the sample standard deviation. There was a correction. We gave it somebody's name that I was thinking. I want to say it started with a B, and my brain goes Bestline. I think that's wrong. But the formulas were different because when we look at the difference, the standard deviation here has an N on the bottom, and the standard deviation here has an N minus 1 on the bottom. That N minus 1 is designed to make the item larger to account for the bias in this estimator. This was the one everybody wanted to use, but it turns out to routinely underestimate. So to correct for that, we divide by something smaller, making the number a little bit bigger. And that accounts to minimize our bias. It's not perfect, but it is less biased. Questions? Remember, I said that the estimator itself is a random variable. It has a distribution. If it's got a distribution, that distribution has properties. We're going to say that the efficiency of an estimator is based on the variance in that estimator. A smaller variance means more efficient estimator. What the flip? Okay, wait a second. We're talking about estimating height, right? If I get answers that are, the average height of a person on campus is 6'8", and then I do another sample, the average height of a person on campus is 5'2". And I do another sample, the average height of a person on campus is 6'2". The average height of a 6'1", 5'9". I'm getting a huge bunch of spread, right? The smaller the variance is, the closer I am to the actual parameter. Now, more often here is a key phrase. Because remember, I'm doing this sampling idea more than once. Let me go back to the target idea. If I've got a big variance on a target, what does that mean in the picture of my target? It's going to be spread out, right? But if I have a lower variance, a more efficient targeting system, I should have a smaller cluster. Same page, more efficient, less efficient. I know the target's the dead center of this. I'm more often close to that center than I am here. If I'm lucky, I can find the smallest possible variance and still be unbiased. MVUE, minimum variance, unbiased estimator. I really, 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 really am hoping to find these kind of estimators. My favorite thing is that the three estimators I've already named, averages, standard deviations, and proportions, are minimum variance unbiased for normal distributions. The third main property I would like, I don't quite like the name that the textbook gives this. They're going to call it consistency. Okay, wait a minute. If I were to think of the word consistency, it means the same thing over and over, right? Unfortunately, that's not really what they mean here. Consistent in the mathematical, statistical sense means that you get closer to the right answer, the population parameter, as your sample size goes up. As you take larger and larger samples, your spread gets smaller. You become more consistent. Okay, yeah, I can see that. You become less variable. That's what they're using it as. Not quite the same idea. So our variance gets smaller as our sample gets bigger. Now, if I think about that as our distribution, as our target shot, as I get more and more shots, I could get smaller and smaller groupings as I become a more proficient shooter, right? Whether I'm shooting a bow and arrow or a gun, the more I do it, the narrower that spread should get. I should get better. Consistency here means that sort of behavior. But in terms of my normal distribution, I actually see a picture like this. That first lowest curve here is a distribution assuming a sample size of 5. For my GMAT population, they did that over and over and over. They took a sample of 5 and they took the average and they created a histogram for dozens and dozens and dozens of different samples. And they got this low curve. When I took a sample of 20, I got this curve. Even though I took that sample over and over and over again. If I took a sample of 80, I got this curve. They're all having the same average, 520.78, whatever it was. But the standard deviation of this one is really narrow, and of this one it's less narrow, and of this one it's huge by comparison. So as my sample size goes up, my variance goes down. Once again, average, standard deviation, variance, and proportion all satisfy consistency for a normally distributed population. So this same comment applies to consistency also. Questions? Either no one's got the stones to call me on it, or you haven't made the connection yet. I've repeatedly said this only works for a normal population. But we had other distributions. We had the uniform distribution. We had distributions that didn't look like anything. I gave you a table and said, here's the distribution. Well, crap. What happens in those cases? A really amazing result. I am absolutely stunned. X bar is a minimum variance, unbiased, consistent estimator for the average proportion, for the average parameter in a population. So let's think about the sampling error. What was sampling error again?
Sample minus the average of the population.
It was how far off this is from here. And we just showed pictures of what happens when we change our sample size, right? We had a normal curve that got narrower, which means we're changing the standard deviation. But since this is the standard deviation associated with X bar, I'm going to write sigma sub X bar. And we're going to call this the standard error of the mean. Because it's a sampling error. It turns out that this comes from the standard deviation in my population divided by square root of sample size. So as n gets bigger and bigger and bigger, this becomes more consistent. My favorite result in statistics follows. The central limit theorem for a mean. If a random sample is drawn from a population with mean mu and standard deviation sigma, then as n increases, the PDF for X bar gets closer to n mu sigma over square root of n. Wait a minute. What the hell is this symbol? What the bleep is this? When I take samples over and over and over again, regardless of what the distribution of those populations look like, the sample of averages looks normal. I found an absolutely amazing video that I want you to watch. I put a link to it on our Canvas page. Down here in our web links section, this bottom one says 3 blue, 1 brown playlist on the central limit theorem. Grant Sanderson does some amazing work as an animator. He does brilliant math videos. And the one on the central limit theorem is one of my favorites. The first two videos in this playlist are of particular use to us. This first one says, but really, what is the central limit theorem? So let's suppose for a moment, I gave you a normal, everyday, six-sided die. And I want you to roll this 100 times and calculate the average of your 100 rolls. It's a fair die. It's not rigged in any fashion. It's a normal cube, and you roll the die. What's the expected value when you roll a die? Right, it's a uniform distribution, right? 1/6, 1/6, 1. So the expected value is 1 times 1/6, plus 2 times 1/6, plus 3 times 1/6, 4 times 1/6, 5. That adds up to 3.5. If you roll this die 100 times, your average should be around 3.5. I don't want you to roll it 100 times. I want you to roll it 100 times and take the average. 1,000 times. And then I want you to plot those 1,000 averages. The 1,000 averages will look like a normal distribution. Sometimes it'll be exactly 3.5. Sometimes it'll be a little high. Sometimes it'll be a little low. It's really unlikely that your average will be down around 1, right? It's really unlikely your average will be up around 6. You could get an average like 2.8 one time. But the distribution is going to be normal. Now I'm going to rig the die. I give you a die that contains 3 3s and 3 6s. No 1s, no 2s, no 3s, nothing. Distribution's really fucked up, right? There's a 50-50 chance of you getting a 3 or a 6 and a 0% chance of you getting anything else. The average on that die should be 4.5. Roll the die 100 times, take the average. Do that experiment 1,000 times. The result is a normal distribution. Grant did this experiment, animated it, and did it on a computer as a simulation for several different dies. Some are rigged really weird. Some are rigged really nicely. Some are normal dice. But no matter what the distribution looks like, you see all these different shapes here at the top? Those are the distributions of his dice. And then he rolls them 100 times, takes the average, and does that experiment 1,000 times. Every single time, you end up with this normal distribution. The central limit, this is a half-an-hour video. Watch it on 1.5 speed or double speed or whatever. Listen to it. It is astounding because the fact that this result works means that whenever I do sampling, which is how we gather data, I get a normal distribution. The normal distribution is the foundational story of statistics. Page 278, there's another picture in our textbook about this. I think the video does it much better. Please, I am begging you, watch this video over the weekend. Because my application is going to be everything I know about normal distributions, which should help you because the homework on distributions that includes the normal distribution is the one that's due on Monday. So watch this video, it'll help. I will see you all on Monday. Have a wonderful rest of your day. Enjoy homecoming if you're going to stuff.